This presentation is a simulation of the characteristics of a DC shunt motor using multi-sim. So the objectives of the experiment or the activity are to record the characteristic of the DC shunt motor under varying load. So the characteristic may be the speed, the torque, the current drawn by the DC shunt motor when it is carrying a load, and to calculate the efficiency of a DC shunt motor. The operation of a motor can be visualized clearly using the Fleming's left-hand rule. So according to the Fleming's left-hand rule, that when a current carrying conductor comes under a magnetic field, okay, so the red line serves as the magnetic field, and then this one is actually the mentioned conductor carrying a current. So when the conductor is exposed or under a magnetic field, so there will naturally be a force acting on the conductor. So Fleming's left-hand rule is a simple and accurate way to find the direction of the motion of the conductor in an electric motor when the magnetic field direction and the current direction are known. So this was invented by an electrical engineer named John Ambrose Fleming. So according to Fleming, in the or when your left hand will be positioned as shown, the thumb will represent the direction of the force experienced by a conductor. The index or the pointing finger serves as the direction of the magnetic field. Okay, so basically the direction of the magnetic field is from north pole to south pole, and then the middle finger represents the direction of the current. So Fleming's left-hand rule is very important in visualizing as to which direction will the DC motor will rotate. So mathematically, the force experienced by a current carrying conductor, if it is placed in a magnetic field, is given by the formula. So the force F is equal to the product of the magnetic field unit in Tesla, the current flowing in the conductor in ampere, and the length of the conductor or wire in meters. So for electric motors, theta is considered to be 90. That is, the force and the conductor are perpendicular with respect with each other. So a DC machine is generally termed as a dynamo. So when a dynamo is given with voltage with the utilization of magnetism, the dynamo will create an output which is the torque. So torque is provided by the rotation of the shaft in the armature. Then all machines that converts electrical into mechanical energy is termed a motor. So this would be the equivalent circuit diagram of a shunt motor. Okay, so depending on the position of the field winding, the motor can be classified as, if it is connected in parallel, okay, so like this one, the field winding is connected in parallel with respect to the armature, then the motor is termed, or the DC motor is termed as shunt motor. But if the field is connected in series, then it will be termed as a series motor. On the other hand, if there is a combination of the shunt field and the series field, then the motor is termed as compound motor. So for the purpose of simulation, so we have here the shunt motor, okay, so which is coupled with a DC generator. So the DC generator serves as the load to the motor. So we try to analyze the behavior of the shunt motor, not of the DC generator, but we also need to look at or understand the effect of the increase in load of the DC generator with respect to the mechanical load of the motor. That is what will happen to the mechanical load of the motor if the electrical load in a generator is increased. So this would be the parameters that will be used. Okay, so for the two machines, the motor and generator, and then this should be the results, I mean data that needs to be gathered from the experiment. So we'll just, okay, so we'll just verify the initially, okay, inputted data later on. Okay, so to gather the data, so we need to, of course, to use the multi-sim to simulate the given circuit. Okay, so again, we'll try to verify the given data, initial data in the table uh, using multi-sim. Okay, so to use multi-sim, okay, so you may, okay, so, okay, so we need to follow or to build the given circuit in multi-sim. So first is the DC generator. Okay, so this one. So we need to have a supply first. Okay, so click power sources, DC power. Okay, and place it, okay, in the working area. Click close. After, change it to 100 volts. Okay, then the voltage or the source voltage is connected, okay, so to the ammeter. Okay, so we need to have the ammeter. So this measures actually the line current, okay, drawn by the motor. Double click and make it as an ammeter by clicking A, then close. Then the meter is actually connected to the parallel combination of the field and the armature. Okay, so to create the DC shunt motor, so click the place electromechanical icon, click machines, and then DC wound field, click OK, and okay, so place it Okay, in the working area. Okay, just like that. And then the field winding is connected in series with the potentiometer. So we can click, or we can have the potentiometer in the place basic button, then click potentiometer, then click OK. Okay, close, and then we need to, okay, so this will be okay, okay, connected or rotate 90 degrees. Okay, so you will have there the potentiometer. Okay, then we can connect the, okay, so you notice the positioning of the potentiometer. Okay, so you look at the position of the arrow. So you can right click the potentiometer and then flip horizontally. Okay, so connect the field. Okay, so and then this one to the ammeter. Okay, so we can neglect actually the meter number 5. Okay, so this actually measures the current flowing in the field winding of the shunt motor. So we will not be needing the data for the field current. So we can short circuit the terminals of the meter. Okay, so that means we can connect directly the terminals, one terminal of R1 to the positive terminal of the field winding. Okay, and then we can connect this one in parallel with. Okay, so and then this will be connected. Okay, so to the other end. Okay, so and then do not forget the ground. So as you notice, the armature terminals, I mean the armature of the motor is connected in parallel with, okay, so the potentiometer, and I mean in parallel with the series combination of the potentiometer and the field winding. So the purpose of the potentiometer is to vary the current flowing in the field winding, so which in turn will vary also the speed of the shunt motor. Okay, so we okay, okay, for the ground. Okay, so put ground, then close, and then connect it to the circuit. Okay, and then for the generator. Okay, so for the DC generator, again, we need to have the place electromechanical DC wound field. Okay, so click OK, and then place it near the or besides the uh, DC motor. Click close. So the input of the DC generator is torque. So we need to flip this one. Okay, for the mechanical torque coming from the DC shunt motor will be given to the DC generator. So we can right click and choose flip horizontally. Okay, so this one. Okay, so for the DC generator, okay, so you have there the source, okay, so used to create the magnetism, okay, so as explained from the previous experiments. So click phase source, power sources, DC power, okay, so the value of which is 100, and then the field winding, okay, so must have a potentiometer also to vary the current, okay, so which in turn will vary the magnetism. Okay, so in a generator, so we try to, okay, so click, okay, so basic, okay, so and then find the potentiometer, okay, so click OK, then close, then rotate this one 90 degrees clockwise. So let's see if the positioning is the same. Okay, so that would be, okay, so we need to flip this one, okay, so flip this one horizontally. Okay, the positioning of the potentiometer would be this one, okay, so okay, then we connect this in series, okay, so with the field winding, and then the terminal would be connected to the positive terminal of the source. Negative terminal of the source will also be connected to the other end of the field winding. Okay, so it will be connected to here. Okay, and then the generator, okay, so the armature terminals of the generator will be connected to the load. Okay, so we'll use the virtual lamp. Okay, so click, okay, so all groups, and then find the virtual lamp. Okay, so this one, click OK, close, and then rotate this one by 90 degrees by right clicking your mouse. Okay, so then we connect, okay, so insert an ammeter. So this ammeter will measure the current drawn by the lamp. Okay, so from the generator, okay, so connect the negative terminal of the armature to the other end of the lamp. Okay, so and then we use the voltmeter. Okay, so this one to measure the voltage. Okay, so 90 degrees. Okay, so the voltmeter will be connected in parallel to the load. So make sure this is an ammeter by clicking A and then close, and then this will be the voltmeter. Okay, so this will be V. Okay, so the straight line means DC. Okay, so this would be, and then we try to connect, or we try to couple the shaft of the motor to the generator. Okay, so we have now the setup for the, okay, generator and motor. So for the lamp, Okay, so try to have 200. Okay, so 200 volts as its rated voltage, and then to measure the speed, okay, so we'll use this icon. Click this one and place it. Okay, so in between the shaft of the motor and generator, okay, you may adjust it. And then to measure the torque, okay, so we click the ammeter icon, current icon, I mean. Okay, so and then you may adjust it anywhere in the working area. Okay, so visible to you. Okay, so then this should be okay. Now we're now ready to simulate the okay, so the circuit, but okay, so before doing it, so we need to try to take a look at the parameters if they are the same as with the given. Okay, so only the armature field. Okay, so this will be 500 milli. Okay, use small letter M. Okay, and then this would be also 500 milli. Okay, so now we'll try to simulate the uh, circuit. Okay, click this icon or just press F5. Okay, double click this one. Okay, and then uh, okay, also this meters. So it displays actually the voltage and the current in the generator side, and then meter number one displays the current drawn by the motor when the generator is running. So we'll try to okay, so let me zoom it out. So let's try to observe what happens or what would be the effect of the magnetism, okay, so in the motor circuit to the speed of the motor. So when the potentiometer is 50%, okay, so that means a certain current is flowing here, okay, so creating the magnetism. So the speed is 1000 radian per second, okay. So if we try to decrease the percentage tapping, so you notice the speed of the motor changes also. Okay, so we try to increase the tapping, the speed of the okay, so the speed of the uh, motor also increases. So basically, the speed of the motor or to control the speed of the motor is to control the current, okay, so flowing in the field winding, thereby controlling the strength of the magnetism. Okay, so as given in the okay circuit, so we'll use okay, so we'll have 70% and 30%. Okay, so 70% potentiometer tapping for the motor and 30% tapping for the generator. Okay, so this is 70% and then this would be 30%. Okay, so the voltage generated is 99.98 or almost 100 volts. Okay, so let's try to okay. So again for the speed, so never mind the voltage. Okay, so just replace V with radian per second. For the torque, just replace A with Newton meter. Okay, so going back, okay, so to the table. So first is we'll try to have Okay, so the generator to have zero load. Okay, so for zero load, okay, zero load means no load is connected to the generator. That means we can remove the virtual load and then run. Okay, so the current, as you notice, the current drawn by the current provided by the generator is almost zero. That is 0.00000001. Okay, so nano ampere. So that's zero because there is no load connected to the generator. Okay, so we'll try to record. Okay, so the following. Okay, so for zero load, 0 watts load, the motor supply voltage is 100. So the current is, okay, so for meter number 1, that is 182.045 milli. Okay, that's times 10 to the power of negative 3. Okay, so the input power is the product of the voltage and current. Okay, so we can, so calculate. Okay, so multiplying 100 times 182.045 to the power of negative 3. That's 18.2045 watts. Okay, so the speed of the motor is given at 1.4 kilo radian per second or 1,400. The torque is given to be 1.4 times 10 to the power of negative 3 Newton meter, 1.4 milli. So to calculate the output power, the mechanical power, okay, so can be calculated using the formula. Okay, so that's 2 pi times n, the speed in RPM. Okay, so to multiply, to convert radian per second into RPM, so we need to multiply it with 30 over pi. Okay, 2 pi n, and then multiplied with the torque. Okay, so the torque is 1.4, milli divided by 60. So that's 2 pi nt. So that's the same formula uh, that we've used in the loaded characteristic of the DC generator. However, the 2 pi nt over 60 formula there is the input of the generator, but for the motor, that is the mechanical power output. So this would be equivalent to 49 over 25, or that would be 1.96 watts. So to calculate the efficiency, so efficiency is power output over input. Okay, so we divide 1.96 divided by 18.02045, then multiply it with 100%. So the efficiency at no load is 10.77%. Okay, so now we'll try to look at if we try to add an electrical load, so to the generator. So first we need to connect the load first. Okay, so again we try to, or we remove the load. just a while ago, since the load of the generator in the first, I mean in the table is 0, so that means there is no load. So you have to remove the load. Okay, so then we double click, change this one to 25 watts. Okay, then simulate. Okay, so we'll try to record again the following. So motor voltage is set to be 100. Okay, so that's constant for constant along the way. Okay, so but the current, okay, so as you look at, when the generator is now delivering load, the okay, so the motor starts to draw bigger current as compared to the previous current, which is 182. So this time that's 244.52. So milli, and then the input power. Okay, so we'll try to calculate it later. And then the speed. Okay, so it's still 1400 radians per second. The torque. Okay, so torque is actually the measurement of the mechanical force. Okay, so provided by the motor, that means if you try to look at the torque now increases, that means when the generator starts to deliver electrical load, that means for the prime mover or for the mechanical source, it means that the generator will now be heavier to rotate, thereby it exerts more torque. Okay, so this time the torque is 5.86. Okay, so and then the output power together with the efficiency. Okay, so we'll try to calculate the output power first. Okay, so for the output power, that's 2 pi nt. Okay, so N is in RPM, that's 1400 radians per second times 30 over pi. Okay, so then times torque. So 5.86 exponential or milli negative 3. Okay, so this would be divided by 60. So you notice that the output power of the motor increases also as the generator starts to deliver electrical load. So the input power is basically the product of the voltage and the current. So that's 100 times, okay, so 100 times 244.52 negative 3. Okay, so that's 24.452. Okay, then we try to calculate the efficiency. So that's 8.204 divided by 24.452. Okay, so that's 24.452. Then multiply it with 100%. So you will have there 33.2 55%. So this would be the uh, table that you'll need to complete. Okay, so you continue with 50 until 200 watts, and then you'll observe what happens to the motor as it starts, or as the generator starts to deliver bigger power to the electrical load.